30 seconds break, and then that's enough. So it's a great pleasure to have Feng Hao Liu, an associate professor at WCECS. He is an expert in cryptography, and if you are in computer science, you either have taken his 327 class, the first cybersecurity course that everybody takes, and if you haven't, then and you're planning to take it next fall, you will meet him. And he is someone who has also given previous CySER seminars, so I'm very happy that he will be sharing about post-quantum security or cryptography. And if you have questions towards the end, you want to ask him. But thank you very much, and take it away.
Okay, thank you for the invitation. So today I'm going to talk about some post-quantum cryptography and some interesting research and the progress and what we can do actually more from the development of post-quantum cryptography. So I will start with some high-level introduction, and hopefully we will go a little bit into the details, and I will also share with you some interesting stories about defend and attack of some post-quantum cryptography developments, and hopefully, you might be inspired to join the defend and attack this type of cycle, and hopefully you can crack a lot of interesting cryptography. All right, anyway, so the most important motivation for cryptography, of course, we know, even before cryptography, we know internet technology, right? So it can build a connected world so that we have wonderful applications. So like online conference, email, social media, so on and so forth. So security of cyberspace is always very important because there can be sensitive data in the cyberspace. For example, if you outsource or store your some photo or personal data in the cloud, you might at some point want to download them, but adversary might be everywhere reading the chat or listening to the channel. So in this case, your private data might be exposed to the adversary. So there can be a lot of serious consequences if things go wrong. For example, if your credit card information is stolen, and then maybe the bank needs to pay a lot in order to deal with this kind of a breach. Okay, so important technology to achieve security of cyberspace is this public key cryptography. And it is the foundation of our HTTPS. And it has been used for email, secure payment, social media, a lot of, and of course your logins. So everything today depends on this this public key cryptography. So in fact, so we have two versions of web browsing. So one is via HTTPS, and HTTP was the original. And today, so this S, the secure version, implicitly is using public key cryptography in this handshake process. So it is very important that, so no matter whether you know it or not, you are using public key cryptography anyway. So, of course, we are computer science or math or whatever, technology students and researchers. So we are not just interested in the surface of public key cryptography. We want to understand what's behind the scene. What's the foundation of public key cryptography? So here, public key cryptography, no matter post-quantum or regardless of quantum, we need something like math problems that are not solvable by even supercomputers. Okay, so we are very lucky to have a few candidates, including vectoring and discrete log. Vectoring this 8 equals 2 times 4. Of course, those are trivial, but if you scale up the problem, vectoring is very, very difficult. Okay, so these problems are not only mathematically interesting, they actually are widely used. So we know RSA crypto system is based on factoring, and Diffie-Hellman key exchange is based on another problem called discrete log. So because these problems are highly used, well known theoretically and practically, so those the inventors of those two crypto systems won two different Turing Awards. Okay, so Turing Awards are the most prestigious award in computer science, because in computer science you should know that there is no Nobel Prize. So please, don't say like someone won a Nobel Prize in computer science. That doesn't make sense. And similarly, you should know in math there is also no Nobel Prize. Anyway, so however, this foundation is challenged. So what does that mean by challenge? So in 1994, Peter Shor, a professor at MIT, he came up with a polynomial time algorithm, quantum algorithm, to solve factoring and discrete log. So this development was back to 1994. So maybe even before, some of you were born. Okay, so theoretically, this implication is very strong. So what does that mean? So this means quantum computing is more powerful than classical computing, because for classical computing, we don't know that whether there is a polynomial time algorithm to solve factoring and discrete log. We think there doesn't exist such an algorithm. But for quantum, yes, there is a quantum algorithm. So this is a very, very large separation between the power of quantum and non-classical computing. So the implication says if the adversary can build such a quantum computer, he can crack the RSA and Diffie-Hellman. So this could be a cryptographer or like our nightmare of security. But in fact, so during these past 30 years, this nightmare is not a reality. So why? So because the technology was not there. So after he proposed this algorithm, after years of efforts, finally people built a quantum computing in 2001, which can factor 15 equals 3 times 5. But of course, this is kind of very trivial. Your little brother can do that. So this is not practical, because this is not the quantum computer was not scalable. So it can only solve something trivial. Okay, so since 2001, of course, we know technology would well advance anyway. So there are a lot of efforts towards building larger quantum computers. And in today, if you are playing with some kind of investment, you will see a lot of companies or startup companies. They claim they are doing quantum computing, and they raise a lot of money. Whether this is true or false, we don't know, but they anyway raise a lot of money. So let's look at something a little bit more promising. So this is the developments, including IBM and Google and many. So as you might already learn from the previous lecture, that number of qubits can be a measure of how large a quantum computing is. So we know 1998, 2-qubit system, and after several years, we grow the number to something like 50. And in 2019, there is a quantum chip developed by Google, and they demonstrated for the first time called quantum supremacy. So what does that mean? So quantum supremacy means there is a problem that quantum computing can solve noticeably faster than classical computing. Okay, you say, okay, I already know factoring is such a problem. Okay, quantum computing can solve it polynomial time, but the classical computing cannot. But the problem is you cannot do experiment really showing quantum computing break RSA, but classical computing cannot because there is no such a scalable quantum computer. So, but in 2009, Google developed such a very interesting quantum chip, and it can solve some kind of sampling problem in kind of just a second. But if you want to simulate this quantum this distribution generated by the quantum computer, it might take years. So this is the first time that we can see quantum computing doing something. Whether this thing is useful or not doesn't matter, but doing something faster than classical computer. Okay, and since 2019, there are some kind of progress, and maybe by 2030, hopefully, at least for those startup companies, they will draw a big picture saying like by 2030 we can build some 1 million qubit system. But anyway, so still, whether this is promising or not, by 2030 you will see. But on the other hand, what if they succeed? If some company can build, or if the United States or whoever can build a quantum computer like that at such a scale, and they can break the currently in use, say RSA or Diffie-Hellman system. So this means your say secure payment, your social media can be like cracked, and there might not be any privacy at all. Okay, so in order to deal with this, NIST, National Institute of Standards and Technology, they kind of proposed an effort called post-quantum cryptography standardization. So this effort was initiated in 2016. And so the goal of post-quantum cryptography is to develop new encryption or signature algorithms to defend against quantum computing. Okay, so before 2016, people have already studied post-quantum cryptography, but researchers can study, professors or mathematicians, they study, but in order to deploy things in practice, the scope is much beyond what academia can do. And another thing is, if for any university claims some kind of secure algorithm, and no industry will kind of adopt that. So why? Because they kind of need some kind of liability. So if this algorithm fails, we need to have someone to blame. So the thing is, NIST is such an organization. They had this call for proposal, and people have studied a lot intensively about those algorithms, and through a series of competition, and finally NIST will decide several candidates to be standardized, and in the future people can use those algorithms. So and this is not just say NIST, it's not just universities. Also, there are a lot of industrial partners participating in this post-quantum standardization process. So right. So at this moment, we kind of understand that traditional cryptography is facing some sort of crisis because, say, it might be obsolete eventually at some point, assuming like those quantum computing people are smart enough, they can really build quantum computers. So now it is a critical time to think about, okay, can we develop new sciences? So one thing is, can we develop new foundation for post-quantum cryptography? And from there, can we do even more? Okay, So my research is basically kind of aligned with this this logic. So the basic mission is to participate in this rebuilt crypto system against quantum computing. And so this is called post-quantum cryptography, as you know. And this is very important for future security of internet applications. And using this foundation, I also envision a more efficient and richer crypto capabilities. This including computing unencrypted data application to something kind of private machine learning and data analytics, and there are numerous advanced crypto designs. But anyway, so today we will mostly focus on the basic mission, and I will show you a little bit about like those advanced, say, capabilities, so that we know, okay, what we can do beyond, say, just public key cryptography. So let's talk a little bit about some background and the methodology that people care about, how to develop cryptography and post-quantum cryptography. So forget about post-quantum. Let's think about cryptography in general. So what do we want for cryptography? So there are two questions that we must ask. So what is security and how to achieve security? So those like what and how, those are very important. So what is security? We need to think, okay, no attacker can break the system, but mathematically, what does that mean? And how to achieve security? So a question is, say, can you imagine how many attackers, how clever an attacker is? So there can be infinitely many different attackers, different attacking strategies. So how do we defend against these infinitely many possible attacks? So these are two questions, two big questions that cryptography need to deal with, no matter post or pre-quantum. So for modern cryptography, people have developed a kind of a framework to address those two questions. So first, we need to define a very clear secure goal or security goal. So in this example, I'm going to talk about secure channel. So secure channel, there are always two parties, right? So this party party A wants to communicate some private message to party B. And but this channel might be listened by some kind of attacker. And so the goal is to confuse the attacker. So the attacker learns nothing from the channel. So this is kind of very high level, but we want to try to define what it means by he learns, say, nothing about the private message. So define security is very important. So now we have this, already have this private channel, this goal, but we want to define security. So we need to formulate a notion that captures secure channel. So one idea is that the adversary cannot recover the plain text from sent by the sender. And in this particular case, the sender is the Princess Leia. Okay, so in this case, is this notion good enough? So, well, if we just require that adversary cannot recover the whole plain text, this is not good enough, because what if the attacker can retrieve partial plain text? And in this case, this security guarantee is too weak, right? So in this case, the adversary can already identify, okay, this message is dangerous. Dangerous in the adversary's view. So what we need is the attacker cannot learn anything from the communication. Cannot learn anything. So what does that mean by cannot learn anything? So cannot learn anything is the attacker cannot distinguish whether the sender is sending the orange message or the blue message. Okay, so in this case, orange message is kind of bad to the adversary, but blue message is good to the adversary. But the adversary cannot tell which message was sent. Okay, so if this is the case, then definitely adversary cannot learn anything from the from the sender's message. Okay, so this notion was defined by Goldwasser and Micali, and they won another Turing Award. Based on their great study of foundation of cryptography. And by by 82, they proposed this notion, and in the current NIST post-quantum call, they explicitly require that you need to satisfy those notions defined by Goldwasser and Micali back to 82. So those notions are not just theoretically interesting, they are necessary in the future standard standardization. Okay, how to realize this type of security code? Because we don't assume that there is any physically secure channel. So the idea is we realize the channel using math, and this tool is called encryption. So you think of this this drawing R2D2 as math. So kind of this math encapsulates the message. And even if the adversary can grab the mathematical object, he cannot distinguish whether the math encapsulates the orange message or the blue message. Okay. On the other hand, the receiver, if he has the right secret key, okay, he can decrypt. So this is what we want. Okay, so how can we prove security against infinitely many attacks? So there is a very important framework called the reduction framework. So the reduction framework contains 3 pieces. So one is hard math problem, and the second is design, and third is reduction. And reduction is also known as proof of security. So the relation looks like this. We have a crypto system, so this is design. We have math problem, and we want to show a reduction saying that if an adversary can break the crypto system, then there exists another reduction that can solve the math problem. Okay? So if you flip this argument in contrapositive way, contrapositive is like P implies Q, not Q implies not P, so they are equivalent. So the equivalent statement is, if the math problem is not solvable, then no adversary can break the system. The crypto system is secure. So so you don't need to think about like how to attack the crypto system, because there is no way without breaking the math problem. So unless the math is broken, then the crypto system remains secure. So this is kind of very, very powerful framework, and so that we don't need to analyze all different attacks against the crypto system, go to the fundamental math. Okay, so now, do we have some candidates that we can, so the math problem is hard. We can have crypto system, we can have reduction, 3 pieces. So the answer is yes. So we have RSA problem, discrete log problems. So fortunately, we have those problems, but unfortunately, we don't have so many problems like that. But anyway, we still have those 2 problems. Okay, so in the quantum area, so what goes wrong to this picture is the quantum computing can kill the underlying hard math problem. So this problem becomes easy. So if this problem becomes easy, then then the foundation of crypto system is broken. So there is no foundation for this crypto system. So in order to deal with that, so what we need is new hard problems against quantum computing and new design and proof of security, because if the problems are changed, and you might need to redesign the crypto system and also proof of security. Okay, so but before we go to like those new math problems, we need to think about what crypto lessons we have learned. So theoretical foundation for the pre-quantum like settings mattered. So why? Because the first thing we learned from the traditional or theoretical pre-quantum cryptography is this modular design. We want plug and play. So what does that mean by plug and play? So we kind of formulated public key encryption, like a formulation. So an abstract of PKE, security, and the interface. So by using the interface and security, we can already derive some secure applications. Okay, so the next thing is we think about how to realize this PKE abstraction. So from RSA and DL, we know how to like realize. But if this is insecure or these problems become easy, then what do? We consider new math. And as long as we can realize the same abstraction, then we don't need to change anything on the right-hand side. Okay, we just need to change this part. Okay, so it's just like you have a function, right? And your application calls this function. And if this function is implemented in a bad way, you just need to re-implement this function by another secure thing. You don't need to change the whole thing. So this will give us kind of minimal change, okay, in order to say develop new security like say applications. So this is very, very important. So this type of thinking and modular design. So this is something I call. So one thing is our 327 is very important because we kind of want to learn this type of framework and how do we say how to study the public key encryption abstraction, security and security properties, and how to use and how to realize. So we develop things step by step and in a modular way. Okay, so this is some basic. So now let's go to some recent progress about NIST. So we all know NIST aims to standardize future post-quantum cryptography. So one argument proposed by NIST is you might think, hey, I propose a new system and people use it tomorrow, but usually this won't happen. Okay, so if I ask you, hey, your iOS, this version is no good, by tomorrow you are going to upgrade or update, whatever you want to call, but usually by tomorrow, then maybe half of you might upgrade. Okay, so so deployment, migration, in practice, this is a very, very difficult process. And difficult, it means like there are a lot of technicality and then a lot of money. Okay, so I have talked to some industrial partner, people, and saying, hey, now like this NIST, they have this post-quantum core, and I got some feedback. People often ask me like how long or what's the deadline that we should like migrate. Then before that, I don't want to do anything. Okay, so this can explain why it might take more than 20 years to migrate. And another thing is even if some computers move to the new system, but you need to consider compatibility. So if you go to an old ATM and that ATM is not secure, and but you still want some money, are you going to like withdraw money from that old ATM? So this is kind of very tricky problem, right? So of course, at some points, old system will become obsolete, and no one should be able to use those old system. But in the meantime, like many interesting and vulnerabilities can happen. Okay. So there are some challenges. We know it's very hard to find plausible math problems. And even if you have those problems, how to set specific parameters, how to implement, how to deploy, those are a lot of problems, different problems. Okay, so, but at least the first step is, anyway, we need some new hard math problems to start with, because if you don't have math, then you have no way to start. So from the NIST call, there are a lot of different, maybe not a lot, but because we cherish each individual branch. So actually only code-based, lattice-based, hash-based, isogeny, multivariate, and more, and maybe only a few, but not too many. So we only have a few directions that are plausible, okay? And so for NIST, so NIST, they do this competition, call for standard by competition, round by round. Okay, first round submission and try to eliminate several, and go to second round, eliminate, and go to the third round. And from third round, they have identified one public key encryption, three different signatures to be standardized. So this is around 2023, so not quite recent. And from the category point of view, Kyber and Dilithium and Falcon, they are lattice-based. And this Springs, that's hash-based. Okay? So after the, say, 2023, NIST had selected several algorithms, but you can already see most of them are lattice-based, and for public key encryption, there is only lattice-based. So NIST is saying, hey, we cannot just put all the eggs in the same basket, so we need a fourth round, okay? And particularly, we focus on something non-lattice-based. So because lattice-based cryptography has been, say, studied in a more comprehensive, more well-studied, but that doesn't mean it is always, I mean, we hope it is secure, but we cannot put all our bets there. So NIST, in the fourth round, they selected another code-based public key encryption, and this just happened in 2020, I mean, this year, and maybe a couple of weeks ago. So a lot of things going on this selection process, and the theory, practice, attack, defense. So one thing you might be interested in is like, I call it sleeveless cryptographers. So what does that mean? So many candidates were broken during the process, okay? So Rainbow is a multivariate signature scheme, was broken in crypto 2022. And there is this cycle. This cycle is an isogeny-based, say, encryption scheme. And it was kind of considered very promising. But unfortunately, it was broken in Eurocrypt 2023. And this is a very a very significant break, because it is not just I break this particular parameter. The attack is a polynomial time attack that can kill no matter how you scale it, I kill it. So this attack is very, very significant. And my previous colleague, they proposed and they had a lot of proposal and implementations building like a hardware optimization for this particular cycle. So it's very fortunate for his students because his students graduated just right before the attack was announced. So they still implemented something not breakable at that time, but after a month, their PhD thesis was broken. But anyway, so still plausible lattice hash code. Perhaps isogeny is still plausible, but it's hard to say. So now I want to talk a little bit about lattice-based cryptography. So one thing is because that's my area of expertise, and second is because you have already seen there are several candidates based on lattices. So we want to understand what is a little bit about lattice-based cryptography. So lattice-based cryptography basically is you build cryptography based on some hard lattice problems, and there are a lot of interesting properties about lattice. One is efficient operation, and plausibly it is resilient to quantum computing. So at this moment, we don't know any algorithm that can, including quantum algorithm, that can solve lattice problems, and it is a very solid foundation for public key encryption and more, much more. Okay, so that's why lattice-based cryptography is very, very interesting. And one thing that I would like to emphasize a little bit is we know that quantum computing is more powerful than classical computing. That's something true. But can quantum computing achieve exponential speed up for any problem? The answer is no. So because if quantum could, say, exponentially speed up against any classical algorithm, then quantum algorithm could have broken all the post-quantum hard problems. And this is definitely not true, at least for today. So even the most, promising researchers in quantum computing cannot come up with any quantum algorithm against lattice problems. And another thing is lattice problem is in MP, but not MP hard. Okay, so at this moment, quantum computing cannot solve MP hard problems, and because there is something not MP hard, but the quantum computing cannot solve it, and this includes all the problems here. Lattice hash code, perhaps isogeny. Okay, they are not MP hard, but quantum cannot solve. Okay, anyway, so for lattice-based cryptography, we need some kind of new problems, and a problem is very interesting called learning with errors, and this is a problem proposed by Regate back to 2005. And this problem was motivated by, connection between cryptography and machine learning. So I will talk about this learning with error, the problem a little bit, and then we go from there. So by learning with error or LWE problem, we can construct public key encryption signature key exchange, and we already know 3 variants are standardized by NIST. So there are several advanced capabilities that LWE can achieve. So one thing is called fully homomorphic encryption. So what does that mean? So suppose the user encrypts some kind of data, and this data can be, say, outsourced, encrypted data can be outsourced to the cloud. The user can request some computation, and the server, even if the server doesn't know the data, but the server can compute the function on the encrypted data and obtain encryption F of data, and the user can decrypt and learn F of data. And fully homomorphic encryption allows computation of arbitrary F, so any F. So, and this ability is called homomorphic computation. And then there is a very elegant application to multi-party computation. So there was a problem called millionaire problem. So the millionaire problem is say I have a number, you have a number, and we want to compare who is bigger. But I don't want to tell you my number. You don't want to tell me your number. You can think of the number as your account. I mean, your balance in your account. We want to compare who is richer, but we don't want to reveal who is richer. I mean, who has how much. So a solution is I encrypt my number, and you homomorphically compute who the comparison function, and at the end I know whose number is bigger. So this is traditional problem, and more a modern problem I will call is machine learning as a service, where the user has some kind of data like a picture, and the cloud has some kind of model or some neural net, and the client might want to say, hey, do some analysis on my data, but I don't want to tell you what the data is. So is this doable? And the answer is yes. As long as you have fully homomorphic encryption, this is doable. Okay, so say from the LWE almost, we can do a lot of interesting things. But so in place of this LWE, there was a Gödel Prize, so the kind of very prestigious prize in theoretical computer science given to Regev. And if LWE has further impact, then maybe Regev can sleep at home and wait for his Turing Award. But anyway, so let's see. Okay, so what is learning with error? So let me, because of the time, so we need to quickly go through. So this learning with error is the problem where there is some secret vector S. So the user has kind of a click, and when she clicks, she learns a random A1 and A1 inner product with S plus some sort of error. So she can do this multiple times. At the end, she receives she can collect those A's, become a matrix A, and a B, vector B, which is AS plus some error E. And the goal is to find the secret vector S. So this is kind of machine learning type of thing. So you learn some samples, and at the end, you want to figure out the secret. So if there is no error in the picture, then you can use Gaussian elimination and figure out S. This linear system, nothing difficult. But if in the presence of the error, even powerful quantum adversary cannot learn the secret. Okay, so that's very, very impressive. Okay, so, but currently, if we use LWE, there are some drawbacks. We know how to construct public key encryption, but the parameters are super large and not very practical. So one thing is I kind of did a quick calculation. So the public key length of original LWE is 1 megabyte, but if you want to compare with pre-quantum RSA, which is 4K bits or 8K bits, say this 1 megabit bytes is super large and it's not very practical. So if we want to do this, then so one research is to improve the efficiency. But so to improve efficiency, we know we want to introduce more algebraic structure and use some sort of rounding instead of generating noise by some distribution. But anyway, So those are just some high-level things, but the fundamental question is, if we want to add those variants, efficient variants, will that affect security? Okay, because crypto is sensitive. So some of my research is to show that these variants are as hard as some lattice problems, so that if we want to accelerate, improve efficiency moving to those variants, then that can be a very good, approach. Okay, so finally, let me talk about some interesting challenge and visions. So I just mentioned sleepless cryptographers, right? So this also applies to LWE as well. So April 10th last year, Chinese researcher Yilei Chen, he claimed a quantum polynomial time algorithm that solved LWE. Okay, so that's April 10th. And that kind of created another super nightmare for a lot of things, because at that time, NIST had already selected Kyber, dilithium, those lattice space candidates. And if this is true, then this is kind of big hammer that will crush all the efforts of NIST and maybe a lot of interesting proposals, including mine. But anyways, he proposed a 9-step algorithm. And it was posted on a very important archive called ePrint. That's a very prominent place where people can, before publishing their paper in a peer review place, they can publish here. Okay, so the implication, if true, I mean, if his attacks are valid, then this will attack a lot of different things. And the public key encryption and signature submitted to NIST are not affected because of the parameters, but this will cast significant doubt on the whole branch of lattice-based cryptography. What if you just optimize Yilei Chen's attack and then you can break those candidates? So a lot of discussions going on, and 8 days later, a fatal mistake was discovered. So the implication is LWE and their variants remain post-quantum secure. So very interestingly, the fatal mistake happened in the last step of the algorithm. Okay, so the first 8 steps were valid, and only the last step. And of course, you might think, why don't you just patch the algorithm? And of course, if they could, then one called a fatal mistake. So no cryptographer, mathematician could, at this moment, patch the mistake. But maybe you can. So anyway, so the vision is, we know LWE, on the plus side, we have a lot of security foundation. Say we can do software, hardware acceleration, and there are a lot of new algebraic techniques to improve security and the speed or whatever for public key encryption, fully homomorphic encryption. A lot of applications for LWE. But on the downside, we cannot just look at the positive. We also need to look at some negative. But negative can also be turned to the positive if you can make the algorithm great again. So this, if you want to put it in short, that's also mega, but in a different context. But anyway, if you can make the algorithm great again, you will probably at least win another Gödel Prize, and you will kill a whole branch of, cryptography, and that includes my expertise, and that can be very cool if you can do that. Yeah, okay. Anyway, so according to another, this person is Micali. So if you remember, Goldwasser Micali, they defined the security of cryptography, they formulate a security property we want. So he won 2012 the Turing Award. So he said, science wins either way. So no matter which way is true, at least science wins. Okay, so this is my presentation, and thank you very much.
We have time for questions. That was an awesome talk. We have time for questions. While they think for question, I want to ask you something about the NIST thing, right? And so they want to standardize. And so there was these rounds and there were proposals, and then they say, let's select what's round two, let's select more, eliminate. That's the word you used, eliminate. And one thing that struck me was that I know there will be things that will be good to eliminate, right? But if you keep on eliminating and then you've got it round four now, the assumption is all the good ideas were there to begin with. And so in the proposal, so I was struck by that. Why wouldn't they invite even newer ones in?
So in round four, they invited new proposals. So whereas they eliminated because they didn't advance to the next round, it's just like, for example, like this NFL postseason. So if you go to postseason, but you didn't win Super Bowl, are you a bad team? Well, that's not right. We cannot say something like that. But it means someone is at least better in some games. So so if a scheme is eliminated at some round, well, does that mean it's not impactful? Not necessary, because at some point maybe people can come up with something from there and maybe like go to another new scheme to be standardized. So this kind of is like an adaptive process. So before, so when we had say standardization, first RSA and Diffie-Hellman over like ZP are like standardized, and at some point elliptic curve was discovered, which says, okay, your key can be much smaller. So at that time, like elliptic curve based cryptography was standardized as well. So we never know, but we should not think of elimination as failure. That's not true, but we need to think how we can advance science by this elimination.
Right, that's great. Anybody has got any question? I know it's not maybe easy to answer for you very quickly.
Okay.
But these people or the person whose picture you showed, they said here is the guarantee for security, and that's what NIST would use to to decide what to choose. So what, I know the math is probably difficult, but if you can very intuitively tell myself and the students, what is it that guarantee that makes the 82 the golden prize and things like that? What is it saying intuitively, like that would guarantee that security?
So the guarantee is kind of very, very interesting. Okay. So let's just go back a little bit. So this is the problem. Okay. So one question people have studied or considered is, so we know cryptography, if it exists, it needs to have some hard problem that machine learning cannot learn. Because if machine learning can learn everything, he can learn the secret key by a set of, say, ciphertext. So cryptography exists means machine learning is limited. On the other hand, if machine learning is limited, can we do cryptography? Well, we don't know yet. But if machine learning for this problem is limited in the sense that it fails, it cannot by observing a series of samples, it cannot figure out the secret. Okay, then this problem is sufficient for us to derive cryptography. And whether we have another machine learning problem which can derive cryptography, we don't know. Okay, we don't know. So this is very, very specific. So every problem, factoring, discrete log, they are quite specific. And if we want to say, how do you figure out those problems? Okay, I think I have no idea how people figure out those problems, but perhaps told by someone like some intelligence beyond ours. Okay.
Great. Okay, well, I think we'll stop there. Thank you very much again.